So we've been talking about predicting whether customers are pregnant using transactional data and a few other variables, and I would just want to step away from that problem for just a second to talk about another regression problem. So when we estimated the model coefficients when in the the customer pregnancy data, we use the evolutionary solver. And in some situations, you might use an algorithm that's similar to that evolutionary solver to figure out what your model coefficients are. Now, most of the time when you have sort of small data, let's say you're a professor and I do a study with like 100 students or a couple hundred students, that would not really be considered big data, and I may only have like 5 or 6 independent variables in my regression model. So it's not getting very big, it's not getting very complicated. I can use something else that's called the normal equation. And I can actually find the values of those for those regression coefficients that really genuinely are the optimum, that you can't get any better. And that requires a little bit of what's called matrix algebra. And I just want to give you a little bit of intuitions about what's going on behind the scenes when you do that type of regression. So when, say, you're using SPSS to analyze survey data, or a professor is doing some academic research and using regression to, say, analyze survey data or experimental data, they're probably going to be using the normal equation. If you're in an advertising industry context or using it for marketing or using it for big data purposes, you probably won't use the normal equation. You're probably going to be using you're probably using another algorithm that we'll talk about in a subsequent video. So let's just, for this video, just focus on another data set real quick. It's a super simple data set. Let's say it's about houses, right? And you've got the size of the house in square feet. You've got the number of bedrooms it has, you have the number of floors, you have how old the house is in years, right, in column D, and you have the price of the house in column Y. And you're wanting to predict how much the house is going to cost based off of these other variables. So this thing here, this is often called the design matrix. So, and in the real design matrix, we would actually want to have a separate column over here that's just filled with ones. So you can see, just like we did in the retail mart example with the DataSmart data, we put in a column of ones there called the intercept. We would put a column of ones as well in this, and then we would get that design matrix. And so what does the normal equation actually look like? So I'm going to go over here to this tab. And so we have, let's just zoom in over here. You can see this thing. It says x. So x is this square of numbers. And if we go back to our data matrix, you can see it's just this square here with the dependent variable y removed, just the independent variables. So it's just that with that column of ones that you need, okay? And so that is x, and that's going to be one of our matrices. And then y is going to be this column. So we'll have a column that's labeled y. So we've got x and y, whoops. And then I want to show you what the normal equation actually looks like. So this theta here is the thing that we're trying to get. And by the way, this slide is from Andrew Ng of Stanford. And by the way, he also is a guy who trains self-driving cars for Google, some other companies. And so this slide is from his machine learning course. And it's a very good course. You should check it out if you're into this stuff. Let's see here. Close. So this theta here is just a list. That's actually a list of all of our regression coefficients. And that's the thing that we're trying to estimate, right? And then we have, this is an x transpose. So x is that column, or is that square of numbers, that matrix of numbers I showed you just a second ago. We're taking the transpose of that, and then we're going to multiply the transpose of that by itself. And then we're going to take that to the -1. So we're going to take the inverse of, we're going to get another matrix out of this multiplication procedure here. And we'll take the inverse of that. And then we'll multiply that by the transpose x, and we'll multiply that by the column vector y, those 4 values of the house price. So let's go back. So just like, yeah, if this is confusing, I wouldn't worry about it. I want to give you some intuitions about what's going on behind the scenes here. Just to let you know that we're not doing any solving here. We're not using some algorithm that's going to tinker around with values. We're actually using a formula to get the true optimum values for our regression coefficients. Let's go over here. So here's x, as I mentioned a minute ago, and here is transpose x. And as you can see, all that is they've taken x and just sort of turned it 25 clockwise, a quarter turn. And if we take that normal equation and kind of break it down into different steps, we could say, okay, we've got x times the transpose of x, and then we take the inverse of that, the -1, and there's actually Excel functions for all of these steps, and then we take so the inverse of that we're going to represent as b, and we take that times the transpose of x, and the result of that we'll represent as c, and we'll take that times that column vector y. So you can see I've actually done all these processes, these steps here. So I took the transpose of x and I did a matrix multiplication to multiply x by the transpose of x. And then I took the result of that and multiplied that, and got the inverse of that. So took the product of those two matrices and got the inverse. And then took the product of that and multiplied it by the transpose of x, and then took the product of that and multiplied it by the column vector of y, and we get these outcomes here. Now, of course, these were in Microsoft Excel here, and there's tons of rounding error, and these were extraordinarily complex computations, so these are likely to be way off, and you probably shouldn't do a regression with just 4 data points anyways. But just to illustrate the idea that one can use matrix algebra to solve for the optimum values of the regression coefficients, and you don't have to use a solving algorithm. Those solving algorithms come in handy when you have big data, like thousands and thousands and thousands of rows. If you're doing surveys or you're doing experiments or anything like that, where you're only going to have a few hundred rows of data, go ahead and use the normal equation. So if you're using SPSS, the default will be the normal equation, and if you're using statistics software like R and you're just doing simple linear regression, the default will also be the normal equation, and if you use any fancy libraries in R or something like that, you can probably ask for the normal equation depending on which specific one you're using.